Okay, so here's the setup. We have a continuous time signal x of t. Okay. But what we get to observe is only samples of x of t taken every capital T seconds apart. That means I get to know that the value taken by the signal at time t equal to 0, which is namely x of 0. We know that this is x of t, we know x of 2t, so on and so forth. But we don't know the values taken by the signal for the intermediate time instance. Okay. So the question we are interested in is, can we get or can we recover x of t back from just the samples? Okay. If I just ask this question to you, you could immediately tell me that it's impossible, right? It's impossible. In fact, this is nonsense, because I could draw another signal, which let's say I'm drawing in blue. Which passes through exactly the same points as the black signal at the time instance 0t, 2t, 3t, so on and so forth, right? So if I just gave you the values at these integer multiples of capital T, there is no way to distinguish whether these samples came from the black signal or the blue signal. Does it make sense? So you cannot really recover your x of t. When I say recover, I want to recover it correctly, or I want to make sure that there is a unique x of t that resulted in these samples. So clearly that's not possible if I just ask this question to you. I have to put some more restrictions on x of t to be able to recover x of t exactly from the samples. And it turns out that all we really need is for x of t to be band limited. Okay, so now I'm going to change the setup slightly and tell you the following. I'm going to tell you that there was a band limited signal x of t. There was a signal that was band limited to between negative Wm and capital Wm. Okay, and then we took samples of the signal every t seconds apart, and we know the samples. Now the question is, can I recover the signal x of t back from the samples? And surprisingly, the answer to this question turns out to be yes, as long as you sample the signal close enough. I mean, intuitively, what do you think? Intuitively, if you sample a signal close enough, it seems like you're retaining more information about the signal, right? But if I did not tell you that the signal was band limited, no matter how close you sample that signal, I can draw a blue signal and a black signal that would pass through all those points. So it's just hopeless to recover x of t back from just the samples, no matter how close you sample it, if we did not know anything about x of t. But if I told you x of t is band limited to some negative omega m and positive omega m, it turns out that if I sample the signal closely enough, knowing that it's band limited and keeping the samples, I can uniquely get my x of t back. So roughly, what is the intuition here? The intuition is this. If you look at the black signal versus the blue signal, you can see that the blue signal somehow changes more quickly than the black signal, right? So if the signal is changing quickly in time, it means that it has more higher frequency components. So then I could use this information to rule out that the samples could not have come from the blue signal, but it should have really come only from the black signal. I mean, it's not clear at this point that it is in fact possible to recover it, and it's one of the surprising results, I would say. But that's what I'm going to show you now as to how we can get the signal back. When is it possible to get the signal back? Okay, so we're going to be interested in the setup when x of t is band limited and we take samples t seconds apart. That is, what is given to us is the set of values so we can write this as the set of values x of n times t is given to us for all n, all integer n. So we are interested in three questions. Okay. First is, under what conditions when I say conditions, I mean conditions on t and omega m. What is the relationship between the sampling time t and the maximum frequency content of x of t, which is omega m, such that we can recover for x of t from its samples. That's the first question. Yeah. Right. Yes.
But we have a maximum sampling frequency that we could use. We cannot increase, for example.
It's actually a minimum.
At the t.
No, as a sampling frequency. So what's going to happen is this. We're going to be given omega m. Okay. So somebody tells us that the signal is band limited to between negative omega m and positive omega m. So for example, if you are building a phone, you know that you are going to deal with voice signals. You know that you are going to deal with signals which are band limited to negative 4000 hertz or to positive 4000 hertz. So we know omega m. What we are asking is, how small should I make my t, or really how large can I make my t such that I can still be able to recover my x of t from its sample. If I make t too large, that means I am losing too much information. At some point I will not be able to recover my x of t back. Clearly when I make t smaller and smaller, it gets better, but it turns out there is a threshold. If t is larger than some threshold, you cannot recover x of t back. But as long as t is smaller than that threshold, you will be able to recover x of t back. Does that make sense? So typically instead of couching this problem as in terms of sampling instant, we can also ask for what's called the sampling frequency. So we can define 2 pi over t as a sampling frequency. So if I'm taking samples t seconds apart, I can think of the sampling frequency as 1 over t hertz, or equivalently 2 pi over t radians per second. And we can ask the same problem in terms of sampling frequency instead of sampling time. Okay. So maybe I will just write that also. So if that's not a separate question we are interested in, but if omega s is defined as 2 pi over t, then what are the conditions on omega s? Okay. Is this clear? Is the setup clear? Okay. Now, once we establish that it's possible to do something, we would like to know how to do it. Right? How can I reconstruct x of t back from samples? And finally, we can ask the same question in a slightly different way. You know, I like to think of this as kind of an interpolation problem. So think about the reconstruction problem as an interpolation problem. So what do I mean by that? If I only gave you samples of a signal, right, I basically just gave you just these values, and then I told you that the signal was band limited to some negative omega m to positive omega m. The process of reconstructing the signal x of t is the same as trying to interpolate between these values that are given to us, right? Because at integer multiples of t, I know what the value taken by the signal was. So whenever I reconstruct anything, it has to match exactly what I observed at those time instants. But between those time instants, I don't know what the value taken by the signal x of t was, and I'm trying to interpolate between these values. If I just asked you this question, without you knowing any Fourier transforms, without us being in this class, if I simply ask this question to you, I have these samples, I would like to interpolate between these samples, what would you do? How would you interpolate between these samples? Just guess something. Lines, not a bad guess. So you can draw lines between the given values. That would be one way to interpolate the signal. But that's not the only way to interpolate, right? Maybe I can draw some quadratic functions, splines, anything like this. So what is the right thing to do? Okay, my application is that I want to get my x of t back exactly. That's my application. So it turns out, and this is one of my favorite things. It turns out that if x of t is in the answers that all of you gave me, you never really use the prior information that x of t is band limited. Somehow that information has to come in, right? You have to somehow exploit that information to be able to interpolate between these samples. And when you exploit that information, it turns out that the correct way to interpolate is to actually fit sinc functions. And we'll talk about that. It may be a little bit early to say exactly what it is, but this is something that's nice that's coming up. Okay. So the question we could ask is, how can we interpolate between the samples? All right, so we're going to try to answer these questions. So I'm going to first begin by explaining mathematically what we mean by impulse sampling. So we have some signal x of t. The first thing we want to think about is, how do we express the samples of this signal mathematically? So one way to do this is to do the following. I'm going to think of the sampling process as actually multiplying this signal by a train of impulses. Okay, so let me explain what I mean. So here is our signal x of t. If I considered another signal which was p of t. So here is another signal p of t, which is summation delta of t minus nt for n going from negative infinity to positive infinity. So here is 0, t, 2t, so on and so forth. So we have our x of t, we have our p of t, and I'm going to multiply x of t and p of t together to get a third signal, which I'm going to call as x sub p of t. So it's defined as x of t times p of t. Now what would happen when I multiplied these two signals together? What I would get is also a bunch of impulses, but the strength of these impulses would all be affected by the values taken by x of t at time instants which are integer multiples of capital T. right? So I would get something like this. I would get this, I would get something bigger here, something similar, something smaller. So the strength of this impulse would be x of 0, strength of this would be x of t, this would be x of 2t, x of negative t, so on and so forth. So one way to write this mathematically is to write this as summation x of n times t times delta of t minus n times t, for n going from negative infinity to positive infinity. Does that make sense? Because it just says the signal is a set of impulses occurring at integer multiples of t, and the strength of these impulses is given by x of n times t. Okay. So of course now we are given this signal x sub p of t. Now from here we can conceptually think of a discrete time signal which would take exactly the values of x of n times t, but at time instance 1, 2, 3, so on and so forth, instead of t, 2t, 3t, and so on and so forth. Right? There is really no laws of generality in working with this signal. This is pretty much a discrete time signal. We could make a discrete time signal from this. Okay? All right. So now the question is, if we are given xp of t, how can you get x of t back, knowing that it's band limited to negative Wm or omega m and positive omega m? Okay. The insight to this actually comes from looking at things in the frequency domain. It's very hard to get insight into this problem if you just look at it in the time domain. But if you look at what happens in the frequency domain, it becomes very beautiful and very insightful. So let's look at the Fourier transform of all these three signals. Okay. Let's start with the Fourier transform of x. What do we know? I mean, x has some Fourier transform. We don't really care what it is. But what do we know about the Fourier transform of x? We know that it is 0 outside of a certain interval. So let's say this is my x of j omega. This is omega m. This is negative omega m. You agree? Okay, what do we know about p of j omega? We just computed the Fourier transform of p of t in the beginning of this class, and p of j omega is a train of impulses. Do you agree? Tell me where the impulses are occurring and what the strength of these impulses are. Where is this frequency? 2 pi over t. And we also gave it a term called omega sub s. Right? So I will write omega sub s here. And the next one is at 2 times omega sub s. This one is at negative omega sub s. So on and so forth. Please let me know if you have any questions. I think this is important stuff. Are you with me so far? What about the strength of the impulses? 2 pi over t. Okay, so this is p of j omega. what is the Fourier transform of x sub x sub p of t? So remember, we started with x of t, p of t, and then we multiplied the two of them together, and then we obtained x sub p of t. What's the Fourier transform of x sub p of t? It's the convolution of these two Fourier transforms multiplied by 1 over 2 pi. So I have x sub p of j omega, which is 1 over 2 pi times x of j omega convolved with p of j omega. And let's try to draw a rough sketch of what's going to happen when we convolve the two signals. This is where the beauty is. So what happens when I convolve x of j omega with this x p of j omega? Notice that p of j omega is the sum of many impulse functions, right? And convolution distributes over addition, which means I can take my x of j omega, convolve it with each one of the impulses in p of j omega, and then I can add them up together. So if I just look at the impulse that occurs at 0, what happens when I convolve x of j omega with the impulse that occurs at 0? I get x of j omega back, except for the fact that here it's going to be multiplied by 1 over 2 pi, because I want to multiply by 1 over 2 pi here. So what that's going to do is that's going to scale my, so just to make sure we get all our constants clear, let me say that x of j omega is 1 at 0, just so that we can keep track of all the scaling correctly. So now what's going to happen is this value is now going to be 1 over t. So this is actually nothing but a scaled version of x of j omega. You agree? Okay. Now what happens when we convolve these two together? That's correct. Let's do it one at a time. So let's say I convolve x of j omega with just the impulse that occurs at omega sub s. What is that going to do? So that's like convolving x of j omega with a shifted version of the impulse. So that's going to shift my x of j omega. So what is going to happen is I'm going to get something like this. This is centered at omega s. And where is this point going to be? This is omega s minus omega m. This is going to be omega s plus omega m. Do you agree? And what happens when I convolve this with this? The same thing, but in the other direction. So I have negative omega s, negative omega s plus omega m, negative omega s minus omega m, so on and so forth. And this is the Fourier transform. Maybe I'll draw it nicely. So this is the Fourier transform of the sampled version of x of t. Okay. All right. So what does this tell us? Well, what this tells you is this. If the side lobes don't overlap with each other, see, I'm getting many repeated copies of my x of j omega, right? As I have drawn here, the copies of x of j omega are not overlapping with each other. What this means is if I could build a low pass filter, so think about a low pass filter. So here is 0, omega m is somewhere here, and so this is omega c, which we call the cutoff frequency of this filter. But omega c is any value between omega m and omega s minus omega m. It's somewhere here. It doesn't matter what it is. It's something between the two. If I were to filter my x p of j omega with such a filter, what would happen? And in fact, I will say that the gain of this filter, I will make this to be t. So it's an ideal low pass filter. The gain is not 1 but it's t. What would happen when if I were to filter xp of j omega with this h of j omega? It would kill all the replicas of x of j omega. It would scale my x of j omega by t, so that the 1 over t and t cancel out. I will get back my x of j omega essentially. Right? If I got my x of j omega, that means I've gotten my x of t. It's just an inverse Fourier transform. But this is something really remarkable, right? We started only with samples. What we are saying is what? I've lost a lot of information. I take only my samples. I take a Fourier transform. What I'm really seeing there is I'm seeing replicas of my x of j omega. And if I just kill all the other replicas except the one that I'm interested in, I scale it back up, I got my signal back. Okay, but let's think about what might possibly go wrong with this if I don't choose my t carefully. What is the role for t in this? So I have drawn a picture where things work. Suppose my t is too large. Yeah, a big T, yes. So the capital T or the sampling time. So what happens when the sampling time is too large? Not only real close, they're going to start to overlap. So let me draw the picture when t is large and omega s is somewhat smaller, right? So what is going to happen is this. Particularly, what might happen is this. Notice that this is the key thing, right? This point is omega s minus omega m. What you really want is you want omega s minus omega m to be larger than omega m, so that the two of them don't overlap with each other. The two replicas don't overlap with each other. If omega s is not big enough, then what might happen is you might end up with a situation like this. Let's say omega s is somewhere here. And remember, omega s is 2 pi over t. This means t is too large. Then what I would see is something like this. So here, I will never get to observe what that part of the Fourier transform is. I will only get to observe the sum of this part and the part to the left. I cannot simply filter, now I cannot, there is no filter that I can use to completely eliminate the replicas and get my x of t back. Does that make sense? So really what we want is we want omega s minus omega m to be greater than omega m. Or equivalently, we want omega s to be greater than 2 times omega m. And omega s is nothing but 2 pi over t. So we want 2 pi over t to be greater than 2 times omega m, or equivalently we want t to be smaller than pi over omega m. So what this says is, as long as t is smaller than pi over omega m, your omega s will be big enough that the replicas don't overlap with each other. You can simply design a low pass filter to filter out all the replicas and you will get your signal back. Does this make sense? So here we are clearly exploiting the fact that the signal is band limited to negative omega m to positive omega m, because that's what lets us say that if my sampling instant is omega s, and as long as omega s minus omega m is bigger than omega m, they are not going to overlap with each other. The replicas are not going to overlap with each other. And that's true only because x of t is band limited to omega m. If x of t were not band limited, there is no hope to begin with, because x of j omega itself would run everywhere in the frequency domain. No matter how big omega sub s is, there is always going to be overlap with of the replicas. Yeah.
So why not just take one sample at 0
Uh-huh.
and convolve it with that one?
Be careful. I am not convolving with the time domain signal. I'm okay, good question. So what I am looking here is what happens in the frequency domain for every operation that I am actually doing in the time domain. So if you multiply only by delta of t, if you take only one sample at time t equal to 0, that's like multiplying by a delta function. Multiplying by a delta function will be the same as convolving with a function that's flat, which means you take your x of j omega, convolve it with a function that's 1 everywhere, and that all you will get is the convolved version. You will never get the actual signal back. Yeah, so the convolution is really in the frequency domain. The multiplication is in the time domain. So in some sense, you don't actually convolve it. All you do are operations in time. You take your x of t, you multiply it by an impulse train, you come up with some samples. Now what we are saying is, if I could take the Fourier transform of this sampled version, the Fourier transform would look like these replicas added to itself. Okay, as long as the replicas don't overlap, there is hope for me to get my x of t back. And I can get it back by a simple low pass filter. But now I'll come and answer my second question that I posed. So what it is that I actually have to do in time to get it back? It's clear that we have to do some low pass filtering operation. But what is that low pass filtering actually doing in the time domain? In the sense, if I didn't ever really want to think about what's happening in the frequency domain, what are we really doing with this? That will become obvious in just a couple of minutes. And then we'll come back and close the loop on this. But does this make sense? What's going on? Okay. So before I talk about this, let's spend a little bit of time on this. So this is called the Nyquist sampling theorem. So the precise statement of the Nyquist sampling theorem tells you that if x of t is band limited to between negative omega m and positive omega m, it suffices for you to take samples t seconds apart such that t is smaller than pi over omega m, or equivalently omega s, which is 2 pi over t, is greater than 2 omega m, to be able to recover x of t uniquely from its samples. Okay. This is really a sufficiency theorem in the sense that sometimes you have more information about x of t, saying that it's not only band limited, it might be some other things too. In these cases, you may be able to get away with even slower sampling, which means you could be able to sample even further. But what this says is it guarantees. If you knew nothing about the signal other than the fact that it was band limited, it's enough for you to sample the signal every t seconds apart such that t is pi over omega m, and you will be able to recover it. So really you don't want to sample the signal too fast, right? Because you would like to build systems where the sampling is as slow as possible. Because if you want to sample something very fast, that means you have to build samplers that run extremely fast. You would like to get away with as small sampling as possible. So this theorem tells you you don't have to sample it too fast. It's enough for you to sample it with pi over omega m. And particularly it says, notice that it's inversely proportional to omega m, right? So if you are sampling signals which have small bandwidth, you can sample them very slowly. If you have signals that have very large bandwidth, you will have to take samples quickly. And that also makes intuitive sense, because large bandwidth means there are high frequency components. High frequency components means there are things changing very quickly in your signal, which means you will need to take samples close enough so that you don't miss the changes in the signal, right? but it's just a very nice mathematical way of saying all this. It says it gives a very precise result. It says it's enough to sample this fast. Okay. We'll talk about the reconstruction and then I'll tell you why this result is important. Okay. Now, what did we say about our reconstruction? Our reconstruction process is passing. So think about the reconstruction process. So the reconstruction process involved taking xp of t and passing it through a filter. So let's say the filter has some impulse response h of t. But what we knew is that you want h of j omega, which is the frequency response of this filter, to be an ideally to be that of an ideal low pass filter. So omega c is something that's between omega m and omega s minus omega m. Is it clear to you why omega c has to be between omega m and omega s minus omega m? Because if omega c is less than omega m, that means you are killing some of the frequency components in your desired signal. But if omega c is bigger than omega s minus omega m, you are letting some of the replicas to pass through the filter. You don't want that either. It has to be between these two, and as long as the Nyquist sampling theorem is satisfied, omega s over 2 is guaranteed to be between these two intervals. So you can always choose it to be omega s over 2. Okay. All right, but we'll see. Okay. So if this is the filter that I want, what is the impulse response of this filter? So in the last class we talked about the impulse response of ideal low pass filters, right? So the impulse response of an ideal low pass filter would be a sinc function. Because if you think about the inverse Fourier transform of a rectangle, that's going to be a sinc function. Does this ring a bell? Can someone look up the old result and tell me what the impulse response of this filter is? If I had if the gain of my filter were 1 instead of t, then this would be sine omega ct divided by pi t. But since I want the gain to be t, it would be t times sine omega ct divided by pi t. If I were to write it in terms of the sinc function, this is omega ct divided by pi times sinc omega ct divided by pi. Okay. Now, if I choose omega c to be omega s over 2. So just to be clear, notice that I want my omega c to be between omega m and omega s minus omega m. Now if omega s is greater than 2 times omega m, then omega s over 2 is greater than omega m. So it's clearly greater than omega m, and it will be smaller than omega s minus omega m. So omega s over 2 is a valid choice for omega c. Does that make sense? So it's basically pictorially all it's saying is this: if now if things look like this, omega m, here is omega s, here is omega s minus omega m. Now my omega s over 2 is going to fall right here. because omega s is bigger than 2 times omega m. So it has omega s over 2 has to be bigger than omega m. So I could build a filter that would just filter like this. Okay, this is true only if omega s is greater than 2 times omega m. Okay, alright, so you will see something nice happening when I plug in omega c is omega s over 2. And remember, what is the relationship between omega s and t? Do you remember what omega s is? 2 pi over t. So omega s over 2 is pi over t. So omega c is pi over t, or equivalently omega c times t is equal to pi. So when I plug this into here, the omega c t over pi is going to become 1. So I can simplify it into something extremely nice. Sinc t over t. Oh, yeah, omega c is pi over t, so it's t over. Okay, so let's recap what that means. What that means is this: I go back into my picture here. It means to reconstruct my x of t from x sub p of t, what I need to do is I take my x p of t, run it through a filter whose impulse response is sinc t over t. Now then I'm guaranteed to get my x of t at the output. That's what it means, right? I'm filtering by multiplying by x of j omega means I'm convolving it with my impulse response. I'm passing it through a linear time invariant system whose impulse response is sinc t over t. Does that make sense? Okay. So we will let's write this convolution. Where I am trying to go to is I'm going to try to show you how we can understand this interpolation business from here. So what has become clear so far is that to reconstruct x of t from xp of t, I need to take xp of t and run it through a filter whose impulse response is sinc of t over t. That's what we have done so far. Now what I want to do is I want to just think about that operation a little more, and I want to see what that operation is actually doing, the convolving with sinc t over t. So let's recall that xp of t is something that looks like this. So what I'm going to do is I'm going to take this signal, I'm going to convolve it with a sinc. That's what I'm going to do. Okay? So let's write the expression for that. So xp of t convolved with h of t is summation x of n times t times delta of t minus nt. This is xp of t. I'm going to convolve this with sinc t over t. Okay. Now this is summation over n. Okay, how can we perform this convolution? Well, notice that convolution distributes over addition. So I have a sum of many terms on the left hand side here. I can convolve the sinc with each one of these terms, and then I can simply add them up. So this is nothing but summation x of nt times delta of t minus nt convolved with sinc of t over t. Do you agree? Because convolution convolution distributes over addition. I can move my convolution inside the summation. Okay, what is delta of t minus nt convolved with sinc of t over t? What does this do? What does convolving the sinc by this delta function do? it shifts the sink by n times t, right? That's all that does. So really what that means is I have summation over n sink of t minus nt divided by t. Okay. Now let's try to interpret what this summation actually means. The summation actually means something really beautiful. What it really means is this. So if you go back to the original problem, well, let's see if I can draw it here. Yeah, let's go back to this, my original problem here, and let me just recall that expression. So the expression that I had was x of n times t times sink t minus nt over t, and this was summation over n. Okay, let me try to draw some of these terms corresponding to n corresponding to 0, 1 and maybe negative 1 or something like that. Let me start with n equal to 0. So the term corresponding to n equal to 0 is x of 0 times sink t, sink t over t. Do you agree? Okay, what do we know about the sink function? The sink function is a function that looks like this, but when does the sink function cross zeros? Do you remember? For every integer value of its argument, the sink function crosses zeros. So just to recall, sink will be a function that looks like this. This is sink t. 0, 1, 2, negative 1, so on and so forth. But what is sink t over t? What is that function? What is that operation of t divided by t do? Stretches it out, right? So what that means is sink t over t is a function that looks like this, where now the zero crossings are going to be at integer multiples of capital T. Do you agree? Okay. Now let's go back and think about this term, x of 0 times sink t over t. So the function sink t over t takes the value 1 when t is 0 and it crosses 0 for every integer multiple of t, right? So what that means is this. So here is x of, let me try to draw this in blue. So what that's saying is this. Here is one of the terms from the summation, because it's x of 0 times a sink function. Okay. Now let's think about the term corresponding to n equal to 1. So when n is 1, I have x of t times sink t minus t over t. What is sink t minus t over t? I can take sink t over t and shift it by t units to the right. So what I am really doing is I take my sink function and I am putting it on top of the sample I took at time t. Does this make sense? Now if I do the same thing for the next time instant, I'll just do one more and then we'll I don't know if you can see this green or not, but so x of 2t times sink t minus 2t over t. So that is actually doing this. So the filter is what it's actually doing is this. It's taking sinc functions, putting them on top of each one of the samples that you have. Now you have created many time functions, you are adding all of them up. And now what happens when you add all of them up? You get a continuous time signal. You get all the values in between the sample durations as well. And that's exactly what your x of t is. Okay? But look at the beauty of the sinc function. Wherever you have sampled the signal, you have sampled the signal at 0t, 2t, so on and so forth, right? Any reconstruction algorithm should not mess up these values. When you reconstruct your signal, you know at time t you had a sample. Any reconstruction should not mess this value up, right? Because wherever you sampled it, your things have to match x of t. The sinc crosses zeros exactly where you sampled your signal, each one of these sinc functions. So basically what it says is wherever you have sampled it, I'm not going to mess up those values. Those are all exact. But in between those two values, you are going to interpolate with this sinc function. And the theory tells you this is the correct thing to do as long as you know that x is band limited. This is not something you could have guessed without taking the course. Right? I mean, this is really beautiful when everything comes together. You have your convolution multiplication, you have your Fourier transform of periodic signals, you have properties of sinc, you have scaling of the time axis, shift of the time axis. They all come together, finally tell you can recover your continuous time signal from samples of the signal taken every t seconds apart. Okay? I will assign a project that will involve playing around with this. So tomorrow to class, try to bring your computers. We're going to try to do some MATLAB with this. If you need help with the homework, I will help for some time. But I think it would be nice to play around a little bit with MATLAB. Try to get set for the project that I will assign next week. Any questions? Yeah. I haven't thought that far, but no quiz tomorrow, no quiz next week because we have a midterm next week. And then there's Thanksgiving. So if there is a quiz, there might be one quiz on Laplace transforms, which I will talk about after Thanksgiving.